Let's practice the recursion tree method on one more example. Let's take the recurrence. T of n is 4 times T of n by 3 plus n. We'll start with a single node T of n and expand it to whatever the right hand side of this recurrence says. It says n plus 4 times T of n by 3. So we're going to have 4 children, each with a cost of T of n by 3. In the next round, we will expand these nodes. To expand them, we need to know what T of n by 3 is as per this recurrence. So if we substitute n by 3 in place of n, we get T of n by 3 is 4 times T of n by 3 divided by 3, or n by 9 plus n by 3. So when we expand the recursion tree to one more level, a node of the form T of n by 3 will be replaced by n by 3 and 4 children, each being T of n by 9. Each of these nodes will have 4 children, and all the children will be T of n by 9. We can go on expanding the recursion tree until we hit subproblems of size 1. So at the end, the tree is going to look like this. N will be the root. It's going to have 4 children, n by 3 each. Each of these children will have 4 children, each with a cost of n by 9. And that's because when we expand T of n by 9, we are going to get T of n by 9 is 4 times T of n by 27 plus n by 9. So n by 9 will be the value with which we'll replace T of n by 9, and we'll have 4 children, each corresponding to a subproblem of size n by 27. And then when we expand T of n by 27, we will have 4 subproblems of size n by 81 plus cost of n by 27. So we'll have n by 9, these will have 4 children, each with a cost of n by 27, and so on, until at the very last level, we get subproblems of size 1. So if we mark the level numbers, the root of the tree is at level 0. These 4 children are at level 1. These children are at level 2. These children are at level 3. And finally, the last level is level H. At level I, we will have nodes with a cost of n by 3 to the power I. Right, we have n by 3 at level 1, n by 3 square at level 2, n by 3 cube at level 3, and so we'll have n by 3 to the power I at level I. The number of nodes at each level will be 1 at the 0th level, 4 at the first level, 4 squared at the second level, 4 cubed at the third level, 4 to the power I at the ith level, and 4 to the power h at the last level. And that's because we are dividing the original problem into 4 subproblems. So every time we open up a particular value t of n divided by something, we're going to create 4 children. So the number of nodes at each level will be 4 times the number of nodes at the previous level. Now we need to take the level sums. That is, we need to add up the costs at each level and then add up these level sums in turn to get the value of t of n. So at level 0, the level sum is n. At level 1, the level sum is 4 multiplied by n by 3 because there are 4 nodes each with a cost of n by 3. At level 2, there are 4 square nodes each with a cost of n by 9. So we'll get 4 square multiplied by n by 3 squared. At level 3, we have 4 cube nodes each with a cost of n by 3 cube. At level I, we have 4 to the power I nodes each with a cost of n by 3 to the power I. And at the very last level, we have 4 to the power h nodes each with a cost of t of 1. So we can express t of n as this last term, 4 to the power h times t of 1 plus a summation where in general the ith term of the summation is 4 to the power I times n by 3 to the power I. So n times 4 by 3 to the power I. And I varies from 0 to h minus 1. You can see that if I is equal to 0, the first term is going to be n. And that's what it is. At I equal to 1, we're going to get 4n by 3. And that's the second term for level 1. Now again, we need to express h in terms of n. And we can do that by observing that the size of the subproblem when level I was created was n by 3 to the power I. When we created level 1, the size of the subproblem was n by 3. When we created level 2, the size of the subproblem was n by 3 squared. When we created level I, the size of the subproblems would have been n by 3 to the power I. And when we created level h, the size of the subproblems would have been n by 3 to the power h. Now if we equate that to 1, because h is the level at which the size of the subproblem reduces to 1, we get h as log of n base 3. So if we replace h by log of n base 3, here, and we can take n out of the summation, and we're going to end up with a geometric series again, which will have h terms, where h is log of n base 3. So this series is going to be an increasing geometric series. Because the common ratio here is 4 by 3, which is greater than 1, and the first term is 1. At I equal to 0, 4 by 3 to the power 0 is just 1. 4 to the power log of n base 3 is equal to, if we just swap n and 4, we get n to the power log of 4 base 3. And so this is going to be n to the power log of 4 base 3 multiplied by t of 1 plus n multiplied by this summation, where the first term is 1, the second term is 4 by 3, the third term is 4 by 3 squared, and so on until 4 by 3 to the power h minus 1. So there are h terms in total. So we can calculate the value of that series. This is going to be a times r to the power k minus 1 by r minus 1. A is 1 here and r is 4 by 3. And the number of terms is h. So k is h. So 4 by 3 minus 1 is 1 by 3. And if we have 1 by 3 in the denominator, we can pull 3 up and we get 3 times 4 by 3 to the power h minus 1. So t of n is going to be n to the power log of 4 base 3 multiplied by t of 1 plus n times the value of this summation, n times the value of this summation, which is 4 by 3 to the power h minus 1. So we can write this as n to the power log of 4 base 3 t of 1 plus 3n multiplied by 4 by 3 to the power h minus 3n. Now what's 4 by 3 to the power h? We know that h is log of n base 3. We calculated h in terms of n. We know that h is log of n base 3. So we can again swap 4 by 3 with n and we get n to the power log of 4 by 3 to the base 3. So t of n becomes n to the power log of 4 base 3 times t of 1 plus 3 times n multiplied by n to the power log of 4 by 3 base 3 minus 3n. Now we can add 1 to the power of n here. So adding 1 is going to make it n to the power log of 4 base 3 times t of 1 plus 3n. The power of n will be log of 4 by 3 base 3 plus 1. So what's log of 4 by 3 base 3 plus 1? This is the same as log of 4 by 3 base 3 plus log of 3 base 3. Right? 1 can be written as log of 3 base 3. And log a plus log b is log of a times b. So this is log of 4 by 3 multiplied by 3 to the base 3. And that's log of 4 base 3. So the power of n here will be pretty much the same as the power of n here, which is log of 4 base 3 minus 3n. Now the power of n here is 1. You can see that the dominant term in this whole expression is n to the power log of 4 base 3 multiplied by some constant. We can group together these two terms. We'll get t of 1 plus 3 multiplied by log of multiplied by n to the power log of 4 base 3. Now the power of n here is greater than 1 because log of 4 base 3 is greater than log of 3 base 3. And log of 3 base 3 is 1. So log of 4 base 3 is going to be some number greater than 1. So we can write t of n here as theta of n to the power log of 4 base 3. And you can expect that this is going to be the complexity of the last few terms of this geometric series, because this is an increasing geometric series. And so the complexity of the summation of the series is going to be determined by the last term. The first term is n, and we can see that the overall asymptotic complexity is larger than n. So it's not the first term of the geometric series that's determining the complexity. What's the last term? It's 4 to the power h times t of 1. And we have seen that 4 to the power h times t of 1 is nothing but n to the power log of 4 base 3 times t of 1. So the last term is what is determining the complexity here. Even if we look at the penultimate term would have been 4 to the power h minus 1 multiplied by n by 3 to the power h minus 1. Let's see what that evaluates to. So if we had looked at the penultimate term or the level sum at the penultimate level, we would have 4 to the power h minus 1 multiplied by n by 3 to the power h minus 1. So that would have been 4 by 3 to the power h minus 1 times n. And this would have been 4 by 3 to the power h times n divided by 4 by 3. So we can take this, the reciprocal of this. So this would be 3 by 4 if we pull it up times n multiplied by 4 by 3 to the power h. And we saw that 4 by 3 to the power h is 4 by 3 to the power log of n base 3, because the value of h is log of n base 3. Right? That's what we calculated. And we know that the value of this is log of 4 to the base 3. Oh, sorry. The value of this is log of 4 by 3 to the base 3, where we just swap 4 by 3 with n. So this would be n to the power log of 4 by 3 to the base 3. And when we multiply this with n, this is exactly what we did here. We multiplied this with n. We'll be adding 1 to the power of n. And so the power of n will then become log of 4 base 3. So this is going to become 3 by 4 multiplied by n to the power log of 4 base 3. So you can see that the penultimate level sum is also having a complexity of theta of n to the power log of 4 base 3. The very last term, 4 to the power h times t of 1 is also having a complexity of theta of n to the power log of 4 base 3. So the it's the last few terms that dominate the series, because this is an increasing geometric series, and so the value of t of n is determined by the last few terms, and that value has an asymptotic complexity of theta of n to the power log of 4 base 3, which is the overall asymptotic complexity of t of n.